Good morning, and thank you for joining me today for C++ Contracts, a meaningfully viable product, where I will attempt to present you with a relaxed and sometimes entertaining presentation of some of the more important topics related to contracts in C++26. As to myself, I'm a standards committee member for the past 3 years. I've been particularly active in SG21, the contract subgroup, and took part of most of the discussions in daily telecons and in countless email discussions of the so-called internal reflector. However, I'm not one of the main authors of the contract proposal, also known as P2900. I work at Morphisec, a cyber defense startup which provides automatic moving target defense, in short AMTD, which hides important operating system resources and catches attackers while trying to attack. And also that's coupled with an advanced ransomware solution. I will be presenting contracts, diving only as deep as necessary and where necessary, detailing some of the considerations, the aborted paths, and the controversies over many things along the way, due to very difficult design considerations. I will not be too much of a stickler on terminology or on theory. I will present some of the guiding principles which are part of P2900 and only in proper contexts. And I will be borrowing much of the structure and even code examples from P2900 and from the accompanying rationale paper known as P2899. Now to a quick review of only a small part of contracts terminology. The first type of contract is a precondition. The precondition term itself is the plain language term, while inside the C++ specification, we use the term precondition specifier, which is comprised of the pre keyword, followed in parentheses by a predicate, which is a Boolean expression. If this Boolean expression returns false or throws an exception, then we get a contract violation, as we can see in this example, since the second parameter y was expected not to be 0 and actually passed a 0. Similarly, we have postcondition specifiers. Unlike preconditions, which are evaluated when a function is invoked, when entering the function, postconditions are evaluated when a function returns normally, not when an exception is thrown. And at that time, the postconditions are evaluated. Unlike preconditions, they also have access to the return value. You can see it here as R. You can give it any name you want, followed by the semicolon, by the colons. And pay attention to the const here, which for the first time in the language is important for parameters passed by value. We'll be talking about this later. The collective term for the pre and post specifiers we've just seen is function contract specifiers, or in short, contract specifiers. I will usually refer to them for simplicity as just pre and post. The third and final contract type is known as assertion statements, which is represented in the code by the contract assert keyword. Unlike C asserts, which it directly replaces, it is an expression and not a statement. We'll also cover this later. And of course, it can show up anywhere in the code that any other statement could show up. The collective term of all three contract types is contract assertions. This is the term I will most often be using, and in the slides I will shorten this to CA. Do not confuse this with code analysis. This was previously known as CCA, short for contract checking annotation, which brought upon some objections, and some people thought and what this is not correctly described by the word annotation, which more closely implies something like attributes, which may be ignored by the compiler, which is not the meaning we want to give this in the context of contracts. Also, do note something that has caused some confusion, but no better solution has been found so far, that contract assertions is a term that collectively refers to precondition, postconditions, and assertion statements. However, when we say assertion statement, we only refer to what is represented by contract assert keyword. So we have contract assert as assertion statements, and we have contract assertions, which represents all the three contract types. The C++ Boolean expression inside a contract assertion is known as a contract predicate. Usually, the difference between contract assertion and contract predicate is not that important. So we can more or less freely mix and match them. But sometimes there are important differences, in particular with ignore semantics, which we'll get acquainted with later, in which the contract assertion is considered evaluated, even though the contract predicate is not evaluated because it's ignored, obviously. And now to some bike shedding history, with bike shedding being the quite surprisingly complicated art of choosing proper names in an attempt not to fight to death over them. And do note, naming is very important in a standard. Those names are going to be with us for the coming decades. I've just mentioned the debate over the CCA term, which wound up as contract assertions eventually. This was one of the more heated debates. I have a link for a reflector thread 75 messages long, which is actually not that long in SG21 terms. Along the way, there was a proposal which didn't quite gain traction to name them contract assertion annotations, CAA, but you'll note the word annotation is still there, so that also didn't gain support. I myself proposed contract clauses, something out of real life. There was also obviously some objections to that, so we wound up with contract assertions. Even more heated was the debate over the contract assert keyword, which is actually more important because that's what you all have to live with in the actual code, not just in the standard terminology. We would have wanted to use the assert keyword as most other languages do. Unfortunately, we cannot do that as it would conflict with the existing C macro, which might have a solution in the future, but we don't have one at present with the currently selected syntax for contracts. Therefore, we explored alternatives, and there were over 40 of those. As you can see here, this is the first part. This one is actually mine, CC assert. You can see where the CCA came from. And you can probably understand why this was considered too clever. And this is the second part. The two finalists were contract assert and assert expert. Obviously, contract assert was the eventual winner. I voted against assert expert since I saw it as too closely resembles const expert in a completely different context, which may be confusing. And in hindsight, that was an even better decision than I expected, because at the time, assertion statements were still actually assertion expressions. We'll cover this decision later of making it an assertion statements rather than expressions. So now with them as statements, it would have been a bad idea to name them assert expert, which implies an expression. On now to some restrictions imposed on the syntax of contracts and why we need to introduce those restrictions. A precondition or a postcondition must be placed at least on the function first declaration, which is a location which includes a declaration of the function, which may or may not also include the value of the function. And from that location, no other declaration of the function is visible, hence first declaration. This is what is a term that was previously implied but not explicitly defined in the standard. It is now defined in P2900. The first declarations may differ depending on point of view and point of inclusion. If it's a header file, depending on where it's included for, it may have different, a given function may have different first declarations. Any other declarations of the functions are known as redeclaration, and that includes the function body or implementation. Repeating a contract is allowed, not mandatory, but allowed. We'll cover what that means later. For several reasons, to be friendly to users, if you can repeat a contract, the contract, especially in the function body, then the code becomes more readable. Also, to support functions declared in multiple headers, we wouldn't want to add even more to DLL help. And due to some quirk of friend declarations, that the standard allows their instantiation in any given order, which the programmer has no control over. Preconditions and postconditions, if they are repeated in redeclarations, they must all be equivalent. Equivalent is mostly determined by token equality, meaning the exact same strings, but not entirely. Do have some leeway in terms of names, specifically the names of function parameters and return values, which, as you will note, are two things that are not included in the type system. So you may give the same parameter or the return value different names, but they must refer to the same entity. We'll see next a code example of this. Therefore, the meaning is retained. And for the same reason, those redeclarations and, of course, also the first declaration, as in the precondition or postcondition itself, they cannot contain lambdas because lambdas produce a unique type. And if you repeat the same lambda, even if it's the same one word for word and letter for letter, it creates a new type, and thus it cannot be considered equivalent. Here we have a well-formed renaming. We can see the same parameter named x in the first declaration, y in the redeclaration, but it's obviously the same one. So we have equivalence, and the code is well-formed. Here we can see that the precondition in the first declaration and in the redeclaration, they refer to different parameters. Therefore, this code is ill-formed. On to contract semantics. One of the great controversies of contracts at some points, going as far as endangering contracts in C++26, has been constification. Officially called implicit constness, way too many times autocorrected to you can read for yourself what exactly. The main motivation has been helping catching bugs and avoid contract side effects, which, as you'll see multiple times in this presentation, side effects are something we very strongly discourage in contracts. And P2900 even has a principle to this effect, principle 6, no destructive side effect. We'll talk later about what a destructive side effect is. This is not a clear-cut thing. For example, does a expensive contract check involving many clock cycle, is that something that affects program correctness, as in program behavior, which is something we don't want to do with contracts. Constification is implied on all entities which are external to the contract assertion. That includes external objects, including globals, which were initially not included in this. It also, of course, includes function parameters. The effect is to treat those objects as const, but the compiler does remember whether or not the original object was indeed const, which is reflected if you apply the decal type operator to it. This is very similar to what happens in const member functions. One other thing to pay attention to, and this is nothing new to the language, but it is very much worth remembering, is that we have shallow constness in the language, especially when referring to pointers. If we have a pointer, then constification is applied to the pointer itself, not to the object it points to. Unlike references, where constification, same as const already in the language, does always refer to the object itself, which is being pointed to, as the reference is const anyway, because it cannot be rebound. As we can see in this code example, all the cases other than the pointer case are ill-formed, since they are trying to assign something to the kinds of objects I've just mentioned. This applies to all three contract types. The two cases involving pointers are well-formed, since the assignment is applied to the object pointed to, and as mentioned, due to shallow constness, constification doesn't reach that far. The only currently available and quite controversial way of opting out of constification is by casting away the const via a const cast. Const casts, as you know, are already discouraged, and they may be dangerous. They can lead to undefined behavior. However, it's worth knowing that the undefined behavior actually occurs only if the original object was const. Otherwise, it may be ugly, but in terms of the language, it is well-formed and even safe. So we can see here that all the casting away of constness from I, which was not originally const, are okay. From J, this does run into undefined behavior. Same in the two cases here. In both cases, this is well-formed, meaning it will compile. It is discouraged, but it doesn't lead to any actual bad results if applied to the objects which are originally not const. Now, naturally, constification has drawn many objections. One of them is over the fact that it modifies overload resolution. You can have two functions which are overloaded. And here we have a parameter which is the first time not const, the second time const. They do different things. Now, this can be argued as being bad code, but it does occur in practice, unfortunately. And we would have contracts that basically check a different thing here and here than what regular code checks, which is not subjected to constification. And that raises the question of what is the value of contracts in such cases if they don't check the actual code. Now, of course, this generated a whole back and forth of arguments and counter arguments. We've seen something that can be argued as being bad code, and then the counter argument is okay, but must contracts be useful with real world code, not just have in mind educating the programmers? And that was countered by saying that, well, actually, contracts, one of their main goals is to encourage correct programming practices. Another counter was that if you're worried about creating a different code path and not checking the actual one, then worry about the side effects that would be allowed if it were not for constification. And yet another was that with constification, we get great help in discovering hidden side effects in what were now C asserts, which is an old problem, and now we have an easy way of discovering them, which is indeed happened in some cases. Another objection is over the things that I've described before in terms of shallow constness and the difference in behavior of pointers and references in this regard, which creates some inconsistency, which projects onto contract itself, making contracts arguably incomplete and inconsistent. The counter here is that this is a known language issue and it's nothing new. I am partial as to this, since the contracts do make this a more serious issue. This has been countered by the solution being very hard to do, is creating deep constness would be something very deep, complex to specify, and to implement it would be a new thing on applying only to contracts. There are also objections over usability. There are some widespread types of code which may or may not be necessary from contract predicates. You have C code, mainly operating system code, such as POSIX and Win APIs, which have poor const correctness. And you have things like logging, which are naturally not const, and you may want to do that from constant from contract predicates. And then there are things like the indexing operator in map, which you could argue that it's actually a very good thing that const correctness doesn't allow it, because as you know, that's a known foot gun and may lead to default construction of map elements when a key isn't found in the map. And in those cases, it's better to use map at, which is const. In all those cases, if you do need to have an escape catch, there is the const cast. There are also a couple of other proposed escape catches that apply either to the entire contract predicate or to only an expression which is part of a CA. Especially this operated no const may be considered in the future, because it allows a language solution which would safely provide dropping constness only for objects which are originally not const, and that wouldn't lead to undefined behavior. This is only partly possible with a macro solution. Now on to postconditions. As you've already seen, postconditions have the ability of specifying a name for the return value. That name is only valued inside the postcondition predicate. And that works even if the function returns an unnamed temporary, which means the postcondition becomes the only place where that temporary does actually have a name and can be referred to. This is unique in the capability of being able in this way to refer to any returned value. Up until now, this was only referred for types in which the user can provide a constructor for themselves. The postcondition names the return parameter if you opt to. This is similar to having a reference to it, but not quite. It's like providing an additional name to that entity which is being returned, and this has been likened to structured bindings. It does behave quite similarly to references, but if you were to apply the decl type operator, it would tell you that it is not a reference. As you can see in this code example, I have a postcondition here, and you can see that it fails because it isn't able to validate it as a reference. Const casting away constness in a postcondition is actually a well-defined behavior, even if the result of the function is ultimately assigned to a const variable. And as we can see here in the first example, we have a postcondition which const casts away, and then ultimately this is assigned to a const variable. This is okay, since at the point the postcondition is evaluated, the target variable is not yet bound to the return of the function, and so it's not yet const. Same here. We can see here we have f being invoked. At this point, the result is not yet const, so this is well-defined behavior. By the time it's returned and then the member function foo, which is const, is called on it, we are already past the post condition. So this too is well-defined behavior. As previously mentioned, any function parameter which is passed by value and is ODR used, as in consumed by a post condition in that function, must be defined as const, which is a novelty in the language. Up to now, this const wasn't important because const on by value parameters is not part of the type system. Now it does become important. We'll get to motivation soon. And one point to remember is that this must also be consistent. If you have several redeclarations of that post condition on function redeclaration, you must be consistent with that const. And we see here cases which are ill-formed because we don't have that consistency. In this case, it's in the definition, the function body. In this case, both the first declaration and the function body are consistent with the const, but another redeclaration is not, so this is also ill-formed. The motivation here is actually quite intuitive. If you have a post condition which refers to a function parameter, we must be able to reason about those post conditions and have them and allow them to be sound. If those parameters may mutate during the execution of the function body, then we don't have that capability. So the way out of this is to not allow mutation of those parameters. This must be done consistently, both in function declarations, which are visible from call sites, and in function bodies, which may or may not have a repetition of that contract. And in both cases, the compiler must be able to enforce this restriction. Now, you should note that this const restriction is only ill-formed if that parameter is ODR used in a post condition. And in the future, we may not have that issue once we get capture clauses, which I'm not discussing in this presentation, where we'll be able to capture parameters explicitly and make our intent clear. On to how and when contracts are evaluated and how contract violations are handled upon detection. This is a rough sketch of the sequence of events inside a function in the presence of contracts. So we have the function call, then parameters are initialized. Then we have preconditions evaluated. Then we get to executing the function body, which may include assertion statements if and when they are reached by the control flow. Once we're done with the function body, we initialize. Last thing in the function body is initializing the result object. And then we destroy the local variables and leave the function body. Then we execute any post conditions. And finally, we have destruction of function parameters. And then we bind the result object to the target variable. Now this was designed in this way so that to allow several sequences which are important for contracts. We can see that preconditions and postconditions are both able to see function parameters as they are in their scope between init and destruction. We can see that the result object is initialized before postconditions are executed. Thus, postcondition can inspect and return the objects, but that's done before they are bound to the result object as the call side. So any any const specification here does not apply yet, thus making casting away constness here safe, if you really need to do that. Also worth noting is that post is only evaluated on normal exit. I've already mentioned that. So you won't have that with exceptions at this point, at least. And post is only evaluated after local variables are destroyed, since they may include logic that could affect the correctness of post conditions. Also, this is only specific to Microsoft, as far as I know. The Microsoft ABI destroys parameters on the Kodi side, therefore allowing post conditions to only be evaluated on the Kodi side if they refer to function parameters, whereas other implementations may have more freedom in this regard. Now I get to the very core of the whole contract feature, and that is the evaluation semantics and how they are selected. So we have 4 evaluation semantics, which are classified as checking semantics and 1 ignore semantic. The checking semantics, which are the ones that actually check contracts and evaluate them, they are further subclassified as in the observe semantics standing by itself. And there are 2 terminated semantics, which terminate the program upon detecting a contract violation. Those are enforce and quick enforce, which was originally nicknamed the Louis semantic after Louis Dion, who came up with it. And the ignore semantic ODR uses it's the variables it consumes and must be well formed, as previously explained. When detecting a contract violation, if this happens at runtime, the observed semantic will invoke something called a violation handler, which we'll also discuss shortly. And upon that violation handler, which is a function, upon it returning normally, as in not throwing an exception or doing a long jump, it will continue execution normally. The enforce semantic would also invoke the violation handler, but upon the violation handler returning normally, it will terminate the program in a manner which is implementation defined. Quick enforce does not call the violation handler. It simply terminates as quickly as possible, and with its code needing to have as small a memory footprint as possible. Those are the goals of this semantic. It must be very performant with a very small code footprint. Now at compile time, observe will generate a warning upon contract violation. Enforce and quick enforce are identical. There is no violation handler. They will simply make the program ill-formed. And of course, ignore both at compile time and at runtime does nothing. The contracts feature has been specified so as to afford maximum freedom to implementers to be able to satisfy different needs for different sectors. So with this in mind, there is it's not specified at which build stage contract semantics are specified, or indeed if it is any build stage, they could also be selected at runtime, which by itself allows all sorts of dynamic configurations, having some logger application allowing the user to reconfigure contracts on the fly and so on. Up till now, we used to work with build modes, mainly debug and release. And of course, we can continue doing that. And for example, having enforced contracts in debug builds and having observe or ignore in release builds, but we have any other option that we see fit and that the toolchain allows us to employ. Also, the compiler may actually select different semantics for different contract assertions in the same translation unit, or even different semantics for the same contract assertion during different evaluations. As per P2900, implementations are compliant as long as they offer at least one of the four contract semantics, and that includes the ignore semantic, which means you could have a compliant implementation only providing the ignore semantic, which would imply that no contract predicate would ever be evaluated. Remember that even in such a case, contract assertions are considered evaluated, and they must be well formed at all times to prevent long-term code rot. And they are ODR used, which also entails some possible side effects, especially involving static data members of class templates, which may get instantiated by such contract predicates. Another thing is that the chosen semantic is it's forbidden to ever be detectable by code at compile time, so that such code wouldn't be able to we wouldn't have its behavior potentially affected, which could happen in several ways. You could branch on a if const expr, depending on contract semantic. You could have a value returned by the no accept operator if, as we'll see later, that would be somehow impacted by the presence of a contract. And of course, you could have sphenate if the very nature of the contract in some way would impact which overloaded function would be picked up by overload resolution. On to elision and duplication. Any contract assertion may be evaluated any number of times, including none at all. This is required to maintain decoupling between the caller side and the callee side, each one of which could have any contract semantic selected independently of each other. So you could have both picking up ignore semantics, not evaluating at all. You could have both of them picking up sub-checking semantic, in which case such a contract would be evaluated twice, once on each side. And by the way, this is why we don't like to have side effects in contracts, because then they could happen exactly that number of times. Intuitively, you can see that in most cases, you don't really need more than two evaluation, one on each side. But there is some desire to have this to have more evaluation available for testing purposes, namely testing for contract side effects, which would be more easily detectable the more evaluation you actually perform. As to what the P2900 requires of implementations, the only requirement is to have some upper bound defined. And there are two recommendations, which is to give users a way to configure the actual number of repetitions, and to have by default one single evaluation per contract assertion. Now, unrelated to contracts, and nothing new here actually, elision is where the compiler can prove that some action will not affect the observed behavior of the program if skipped. So then it's allowed by the standard to go ahead and skip it. A well-known example is copy elision. In contracts, the compiler is allowed to elide contract evaluations in cases where it can prove that that the outcome is preordained, and that there are no side effects such as throwing long jump or terminate. The cases in which it can prove that it's preordained, it's either when the uh, predicate on which some conditions and some circumstances is checked at, is evaluated at compile time, or if it's guaranteed by previous contract assertions and under terminated semantics. So for example, if we have a contract assert that stipulates that x must be greater than 1, followed by a check that x is greater than 0. Now, obviously, if x is greater than 1, then it's also greater than 0. The very fact that we are able to reach the second contract assertion here means that we have successfully evaluated the first one, but only if we've done so with terminated semantics. If we had had a violation on the first assertion, then we would have terminated or as we'll see later, skip the following code in some other way, and we would have never reached the second one. So under such a condition, there's no point in now checking also the second assertion. With elision, the compiler may not only eliminate a contract assertion evaluation, it may also generate an equivalent expression instead of the original predicate. Such an expression would have to be to generate the same outcome in all cases in which the original expression is well defined. In cases in which it's not well defined, that would mean it's undefined behavior, and that's fair game. The compiler can do whatever it pleases. If such a replacement takes place, any side effects may or may not be eliminated. Both are okay. No new side effects may be introduced. Now we have principle number 6 in P2900, which says that contract assertions, by their evaluation, they cannot introduce side effects, which so-called destructive side effects, which affect the correctness of the program, meaning affect the behavior of the program, basically. So not only are we discouraging users from having side effects in contracts, but we also don't want to introduce any ourselves. And we can see what may happen with such side effects if we have this piece of code here that has a side effect of increasing, incrementing I. We don't know how many times this precondition is going to be evaluated. So who knows how many times we're going to increment I. So that's definitely not a good thing to do. Now there's a small limitation on the degree of freedom the implementation has here. It can either eliminate all those side effects or not touch them. It can't eliminate just part of them, because obviously that would make a mess of things. Of course, again, we don't want side effects in contract assertions. You can see how many problems they cause. Definitely don't depend on them for your business logic. I mean, you may have some logging or whatever, which it may not be entirely reliable due to how contracts behave, but that's on you. But if your actual business logic depends on this, then well, we might have a problem. Also, not having side effects is what allows us to afford those potentially multiple evaluations, as they are undistinguishable under the ASIF rule from a single evaluation, as long as there are no observable side effects. As to total execution time, which would obviously be impacted by multiple evaluations if those, of course, take any sizable amount of cycle times, is that consider observable behavior that you care about or not? Well, that depends on you or on the and on your context. So there's nothing much to be done there. But obviously, you wouldn't want your contract predicates to be too expensive. Now to the contract violation handler I previously mentioned. So what is it? It's a function in the global namespace named handle contract violation. It takes a single argument of type stud contract violation. It returns void, and it may or may not be no except. Implementations are required to provide a default implementation of this handler, which is recommended that all it does is log in some manner the contents of the contract violation object, and that it be no except. But these are only recommendations. The default handler cannot be directly called by user code. There is an accessor function which allows it be invoked, but in the practice, this can only happen from custom violation handlers, meaning the ones users implement themselves, overriding the default one. And this is because by design and for this reason, the contract violation objects cannot be created by user code. The only way you get your hands on one is if you implement a custom violation handler and get such an object as its input parameter. The mechanism by which the implementation is allowed to enable you to replace the violation handler if it chooses to do so is replaceability, the same as global operators new and delete work. And normal functions don't work this way. Normal function, if you try to replace it, you will get a linker video symbol error because it finds two symbols. But for a replaceable function, you are able to provide a function with the same name and signature as in parameters and return type. It is allowed to differ in the Turing specification, no except versus no except false. And then the function you provided replaces the original default function. So you can do that with the violation handler. The standard library only provides an implementation of the default violation handler. It doesn't provide a declaration in any standard header file. The main reason for that is the no except freedom you get here. Now, as I said, implementations are allowed but not required to provide this replaceability, because on some of them, allowing this might be viewed as a security risk, which they cannot afford. The main motivation for having contract violation handlers is the ability to decouple libraries and applications in terms of what to do with contracts. Both libraries and applications can implement contract assertions, but libraries do not get to decide how violations will be handled, what happens in case of a violation. That's on the application. And that gives the application the freedom to decide whether it wants to terminate, only to observe, and so on. The library provider doesn't need to concern himself with that. The application provider is able to gain this freedom and control what happens in their application. In order to have this possibility, of course, the application is able to provide a custom handler if it so deems fit. Those handlers can only be installed at link time, because it would both be too dangerous to allow this at runtime. And then compile time, it would not be practical as translation units may be compiled at different times and with different tool chains. It would be difficult to do this kind of mixing and the matching. An important thing is that you don't have to recompile everything in order to replace the termination handler. You only need to relink, and that's very important. Contracts would probably be unfeasible otherwise for several reasons. Obviously, rebuilding a lot of stuff takes lots of time. Also, there's lots of stuff that you can't build even if you want to, third parties and so on. So basically, this is a must-have for contracts. As to the contract violation object, it may reside anywhere in memory other than the heap. Having it on the heap, of course, would be prone to memory exhaustion issues, which may cause contract violations, and you can have the termination, invoking the termination handler itself be susceptible to such issues. It's not specified how the compiler can produce the object. It depends on the implementation. They can produce it any way they like. Of course, it must be alive during the violation handler. After all, it's given to it as a parameter. But so must the objects that are accepted. So through it, the contract this object contains pointers to other objects such as strings. One of those strings is a something I tried to partially object to about 2 years ago when I had some security related concern about having source code, source name symbols included in distributed binaries, which may make life too easy for potential attackers. This was eventually dismissed in order to give more freedom to implementers and in the understanding that implementers are likely to provide such configurability to concerned users in any case. Additionally, I do mind the fact that exceptions, as previously mentioned in while evaluating the contract predicate, are caught and handed to the violation handler to handle as it seems fit, as just an additional kind of contract violation. Contract violation handlers contain normal C++ code, same as contract predicates for that matter. And as such, they can return in any of the available ways, including normal return, but also throwing exceptions and long jump. The ability to have a throwing violation handler or to have it long jump was actually something that was allowed along the way in a determined manner when there came a demand from no other than Bjarne himself that we need to have a way, even with terminating semantics, to have some systems not terminating because they can't actually afford termination. So that could be viewed as somewhere of a backdoor, although not necessarily so, because the actually way of looking into this is that the main guarantee that terminating semantics afford is that the following code is not executed. Now, if you have a violation handler throwing an exception or long jumping, then it bypasses the following code. If both long jump and an exception which is handled and doesn't encounter a no except barrier along the way would result in the system continuing execution, but not at the following code, so that guarantee holds. Now, mind you, the compiler cannot know what contract semantic is in play during compile time. Therefore, it must assume, given the possibility of throwing violation handlers, it must assume that any contract assertion might throw. This may affect things such as optimizations and some other things that we'll see shortly. Code bases may also want to take this into account. We're already had for the last decade, we've had the Lakos rule, which says that functions with narrow contracts, as in functions that don't have well-defined behavior for any possible input, are not allowed to be no except. Among other things, because we might want to have some kind of check, including no contract checks, which may want to throw an exception in case it detects invalid input. If any possible input is valid and we have a white contract, then this doesn't count. So we're allowed to have such functions defined as no except. Again, we don't have to, and it's not always advisable. My personal advice is to only place no except on functions that need this, mainly functions that are or may be invoked in the context of either a destructor or a move constructor or assignment, which is basically what no except was introduced for from the get-go. Such an easy question, isn't it? Contract assert false. Is it no except? Sounds like a very simple question, but turns out it's not so simple. And turns out we actually have a prime directive of our own, which says that contract assertions are not allowed to alter the characters of the program, which, as we've already known, means alter visible program behavior. So how does this relate to the question I've just presented? Well, if you have an expression which so far isn't throwing, so it's no accept. Now you add a contract. That contract, as we've learned, could throw if we have a Turing violation handler. So if you choose to tell the truth, you're going to say that now it's no longer no accept, but this may now affect behavior. So you're in violation of the prime directive. So what do we do about this? So as you might have sensed, we have two options here, which are both bad options. We can either tell the truth that the expression with the added contract may now throw, or we can lie about it and say, no, it can throw, although it actually might. And then we are liars, and besides morality, that could also have all sorts of bad consequences. And this was a very long argument what to do about this. In most other similar cases, the outcome of such arguments is to make that feature ill-formed, so that we can introduce it as is in C++26, not support this, having such code be ill-formed, so you can't at present write such code. And we can revise it later after C++26. This is enshrined by Principle 14. But in this particular case, we chose another path. We chose to cheat rather than lie. Sometimes you have different evils to choose from, so you choose a third evil. So in this case, we decided to make contract assert a statement rather than an expression as it originally was, and also as there are in practice the C asserts, which of course are macros, but can be used as exceptions, as expressions. Contract asserts, as of now, cannot. They can only be statements, which is that thing with a semicolon at the end. This makes them, the benefit of this is that no except contract assert false is now actually ill-formed, but it's not directly ill-formed. It's ill-formed because you can't have an operator such as no except applied to a statement. You can only apply to an expression. So this now makes contract assert more limited in this regard than C asserts, but this is quite easily mitigated via immediately invoked lambdas. You can have a lambda which encapsulates the contract assert you want to place. And inside the lambda, the contract assert is a statement. And you use the lambda invocation as your expression, and then you have the comma operator. And what comes after it is your actual expression, which determines the outcome of the whole statement. So this works because this simplification works. You can have a void and then comma operator, and then you get the result determined by I. So to recap, contracts took a very long time coming. Actually, they completed 2 decades since work initially started on them. And that is because they are a very complicated feature. But then, so is C++. So nothing new there, basically. As complicated and the feature rich as they are, you normally don't need to care about I don't know, 90% of all this stuff in your day-to-day. And again, this is the same as C++ itself. You care about what you need to, but you do have a very rich tool set when you do need it. And that makes contract a fantastic tool, same as C++ in general. Huge thanks are due to the many great heroes of SG21 who finally made contracts happen. It was a very long endeavor with a huge time invested in this, with weekly 2-hour telecons and hundreds long reflector threads. Very hard to keep up with actually, but well worth it. And my additional special thanks go to Timur Dumler and Joshua Byrne. Joshua, I'm never sure if I'm pronouncing his last name correctly. Perhaps I can finally learn that. Joshua is the main lead of contracts in Bloomberg, which is one of the main sponsors of the contract effort. And Timur is the vice chair of the of SG21. And both of them put in some serious effort and came up with lots of very useful comments when I asked them to review this presentation. Unfortunately, there was no time left to ask them for a second review after implementing their initial comments. So any errors I might have made are very likely due to this oversight of mine. You're more than welcome to keep in touch via my email and my LinkedIn. And I hope you enjoyed and you learned about C++26 contracts and that you will be using them, and so will all of us. And we now have something to really look forward to. Thank you very much.